This is mathheals.com. If you want to go here to find other links to math videos. Let's take a look at estimating a population standard deviation. And is that really the title of the section? Yeah, it is. It's also population variance, so I'm surprised they didn't include that in the title. Now, the Chisquare distribution is what we're talking about here. It says if a simple random sample of size n is obtained from a normally distributed population with mean mu and standard deviation sigma, then chi-square, that's what that little x squared looking little item looks like. That's a chi-square is equal to n minus 1 times s squared over sigma squared. It has a chi-square distribution with n minus 1 degrees of freedom. Now, characteristics of the chi-square distribution: it's not symmetric. It's not like our bell shape or a normal distribution. The shape of the chi-square distribution depends on the degrees of freedom, just like the student's t distribution. Now, as the number of degrees of freedom increases, the chi-square distribution becomes more nearly symmetric. And the values of chi-square are non-negative. Okay. We use chi-square distribution when finding confidence intervals of population variance and standard deviation. Now, some notation we have here, which has some critical values we're going to find, and these are my own personal ones. I never really have liked the notation that's in the book, so I find students click better with these. Here's our picture. This is what a chi-square distribution looks like, typically, and we have two of them, and we got the main body here, the left tail, and the right tail. This is the left chi-square over here, and this is the right chi-square. Now, to find the critical values, your left chi-square and your right chi-square, you'll find your degree of freedom, which is n minus 1. We've seen this before, but again, you think of the degree of freedom, I think of a simple example of my wife and me. She'll ask where I want to go eat, and I'll tell her Old Chicago, and she'll say, no, we've been there. Tell her Chinese restaurant, she'll say, no, I'm tired of that. I'll tell her the Mexican restaurant in Derby, and she said, no, I don't like that one. And about the fourth or fifth time, she'll tell me where we're going. I really don't have any freedom. She's the one that makes the choice. So there's two of us, so 2 minus 1 is 1, so degree of freedom is 1. And the same relative concept works with data. It's different, but you get the idea. If given a percentage, find the amount in each tail. So if you have 90% degree of confidence, you put 90% in the middle, and you split the 10% into your tails. So each tail would have 5%. Then you find your lookup value. For the right tail, look at the area to the right of the 90% middle. In this case, it would be 5%. For the left tail, would look at the area to the right, which would be the right of the 5% on the left side. In this case, it would be 95%. And then looking at the chi-square distribution table, we're using the degree of freedom and lookup value, find the appropriate values of the right and left critical values. Well, let's take a look at some examples, see what in the world this is saying. Okay, so we've got 90% confidence desired. And n is equal to 15. It says find the critical values. So find the critical values. Well, if I draw my picture, this one right here is my left chi-square, and this one here is my right chi-square. Now that's not squared, so don't think that we take a value and we're going to take it to the second power. We're not. That's just notation. And then this L means it's one on the left, this R means it's one on the right. Well, 90% confidence means we put 90% in the middle, and we split 10% up into the tails, so this will be 0.05, and this will be 0.05. Okay, now our chi-square distribution table. Notice it says area to the right of the critical value. So unlike before, with chi-square we look to the right. So I'm going to find my right chi-square first. So I'm looking at this one right here. The area to the right of that is 0.05. We need our degree of freedom, which is n minus 1, which is 15 minus 1 or 14. Should have had that ready. Okay, so we're finding this one. The area to the right is 0.05 and it's 14. Degree of freedom is over here on the left side. 0.05 is this column. So I go down to 0.05 and I go down to, what did I say, 14? Yeah, 0.05, 14 would be 23.685. So 23.685. Again, I looked the area to the right of this, which is 0.05, and I'm using degree for 14. 0.05, 14, 23.685. Well, let's find the left chi-square. I'm working with this one over here, so I'm going to add up all the area to the right. So I got 0.90 plus 0.05. That gives me 0.95 and degree of freedom 14. 0.95, I look in this column, 14 would be 6.571. And those would be our right chi-square, our left chi-square, and our right chi-square. Let's look at another one of these. It says given 95% confidence desired. So 95% confidence. And n is 21. Well, our degree of freedom would be n minus 1. So we've got 21 minus 1, or degree of freedom will be 20. Drawing our picture. Here's our main body. This is going to be the left chi-square because it's on the left, and this will be the right chi-square because it's on the right. And put 0.95 in the middle. I'm sure I'm not the only one that's used L and R to indicate left and right. But then we take the 5%, split it up into our tails. Who knows? Maybe I even remember it from a book. So those are both 0.025. Okay, so let's find the right chi-square first. So I'm looking at this one. The area to the right of it is 0.025. So 0.025 is this column. And degree of freedom is 20. So 0.025 and 20 come down here, it would be 34.17. Now for the left chi-square, I'm finding this one. The area to the right, you have to add the 0.95 plus the 0.025. So that's going to give me 0.975 and degree of freedom 20. So 0.975, degree of freedom of 20 would be 9.591. Assuming my eyes didn't get off. So those will be our critical values. Well, let's take a look at how to find confidence intervals now. This is a formula for confidence intervals for population standard deviation. We got a lower bound, upper bound, and the lower bound is square root of n minus 1 times s squared over the right chi-square. And the upper bound is square root of n minus 1 inside of parentheses times s squared over left chi-square. So it looks like the three things you need, or four things you need. You need n, you need s, and you need your right chi-square and your left chi-square. And then you have your interval. Now there is no calculated way to do this, so these you have to do by hand. Now for population variance. Lower bound, you see that the formula looks familiar, and upper bound, the formula looks familiar. Just they're missing the square root, which makes sense because we know when you square the standard deviation, it gives you the variance. Well, let's find some confidence intervals. So let's do our third example. I'm not sure if I have room here. Yeah, I bet I do. Okay, so given grades are normally distributed at a college, if a sample of 18, well, that means n is equal to 18, has a sample standard deviation of 2.5. So S would equal to 2.5. Construct a 95% confidence interval for the population standard deviation. A 95% confidence interval for the population standard deviation. Okay, we're going to go up here. We got two formulas. This is the confidence formula for the or confidence interval for the population standard deviation, and this is for the population variance. Well, this one said population standard deviation, so we want to use this. Well, we're given N and S, so we got those. We just need to find our critical values, our left chi-square and our right chi-square. Okay. Yeah, draw my picture. Doesn't matter, how well you draw it. We're just trying to get a visual. Here's 0.95, and we'll split up our 5% in their tails, like that. And this one is our right chi-square, and this one is our left chi-square. Now our degree of freedom will be n minus 1, so it'll be 18 minus 1, or 17. Well, let's first find our right chi-square. Well, if I look at this one right here, the area to the right of it is 0.025, so I'm looking in the 0.025 column, and the degree of freedom is 17. So 0.025, 17, 30.191. Now for our left chi-square. Looking at this one, we look at the area to the right. We have to add up the 0.95 plus the 0.025, so that gives us 0.975, and degree of freedom 17. So 0.975 and what did I say? 17. So 0.975 and 17, we get 7.564. Okay, so formula-wise, it says lower bound, we have the square root of n minus 1 times s squared all over our right chi-square. So we got n, which is 18, minus 1, s squared, which is 2.5 squared, divided by our right chi-square, which was 30.191. Now our upper bound. I'll plug those in the calculator here in a minute. Would be the square root of n minus 1 s squared over our left chi-square. So we'll have 18 minus 1, 2.5 squared, that remains the same. And then our left chi-square, which we said was 7.564. Yeah, let's go plug those in. Okay, so square root, so second x squared. It's probably better just to do that in your head. 18 minus 1 is 17. Times 2.5 squared, 2.5, and I'll press my x squared, divided by 30.191. Enter. Now I'll take it 2 decimal places, 1.88. Then the other one. I'll do second enter to bring up the previous entry. Do my left arrow key. And 7.564. 7.564. And then press enter. And I get 3.75. So then our confidence interval is 1.88 and 3.75. And that's our answer. Again, the interpretation of this is exactly like before. We're 95% confident the true value of the population standard deviation falls somewhere in this range. Save that. Oh, had my legs crossed and crossed a little bit too long. What in the world is this called? Estimate the population standard deviation. Yes, estimating a population standard deviation. Page 01.pdf. Okay, let's look at our next problem. That was number 3, so let's look at number 4. Grab a drink first. Okay. It says given ages are normally distributed in a particular town. If a sample of 25 people, so n is 25, which means, while I'm at it, degree of freedom is n minus 1. So that'd be 25 minus 1 or 24. We know we'll need that. In town have a sample standard deviation of 10.1. So S is 10.1. It says construct a 99% confidence interval for the population variance. So for the variance. Well, if we come up here, this is the formula we're going to be using this time. Well, we need our same 4 things, n, s, and our right chi-square and left chi-square. We have n, we have s, so let's find our chi-squares. Okay, it's a 99%, so we're going to put 99% in the middle. Means we're going to split 1% in our tails, so this is going to be 0.005 and 0.005 here. This is our, it's on the right side, so it's our right chi-square, and this is on our left, so that's our left chi-square. Okay, so the right chi-square, let's start there. We're looking at the area to the right of it, which is 0.005, and our degree of freedom is 24. So 0.005 right here, and 24. Way down there. Okay, 0.005 and 24 would be 45.559. So 45.559. Now our left chi-square. We're going to add up all the area to the right of it, 0.99 plus the 0.005. So we're looking at 0.995 and then degree of freedom of 24. So 0.995, degree of freedom of 24, we'll get 9.886. And that's our left chi-square. Now back to our formulas. Okay, here's our formula for lower bound. It's equal to n minus 1 times s squared and right chi-square. Yeah. Okay, n is 25, so we got 25 minus 1 times s squared, so 10.1 squared, divided by right chi-square, which is 45.559. Now our upper bound, this formula, we're going to have n minus 1 times s squared over left chi-square. So we'll have 25 minus 1 times 10.1 squared over the left chi-square, which was 9.886. Okay. So we got 24. You might as well do the part of that in your head. 25 minus 1 times 10.1 squared. 10.1 squared divided by 45.559. Enter. And I'll take it 2 decimal places. So we got 53.74. Now for the upper bound. I'm going to do a second enter to bring up the previous entry so I don't have to retype all of it. And we'll type in 9.886. So 9.886. Enter. And we get 247.65. So our confidence interval will be 53.74, comma, 247.65. And that's our answer. I don't know if I have room for the next one or not. Let me save this and start a new page. Okay. Here, where it says a sample of stock prices in a particular industry, you've yielded the following stock prices: 15, 18, 17, 13, 14, 16, 15, and 13. 1, 2, 3, 4, 5, 6, 7, 8. There's 8 of them. Well, that tells us n is equal to 8. That's one of the things we needed for our formula, wasn't it? It says construct a 90% confidence interval. So 90% confidence interval for the population standard deviation. For the standard deviation. This is the formula we're going to use. Well, we have the n. We don't have s. So let's find s. So if they don't give you the sample standard deviation, you have to find it. Well, I'm going to put these in a column. These are my x values. So I got 15, 18, 17, 13, 14, 16, 15, and 13. 15, 18, 17, 13, 14, 16, 15, 13. Okay. Well, I'm going to add those together. As soon as I found my calculator, there it is. 15 plus 18 plus 17 plus 13 plus 14 plus 16 plus 15 plus 13. 15, 18, 17, 13, 14, 16, 15, 13 gives us 121. Well, we need x bar, so we're going to take 121 divided by how many we have, and I think it was 8. Yeah. So 121 divided by 8 gives us 15.125. Well, then I need a column, x minus x bar. So I'll take 15 minus 15.125. I'll be doing this here shortly with the calculator, so you don't have to do this part by hand. So we got 18 minus 15.125. We got 17 minus 15.125. We got 13 minus 15.125. 14 minus 15.125. 16 minus 15.125. And then 15 minus 15.125, and then 13 minus 15.125. Now, if you're sitting there calculating these by hand, because you don't have the money for a calculator, or you're being forced to by your instructor, you probably are better off to use the other formula than the one I'm using. So if you go back and look at that particular section on the standard deviation, you'll see the shortcut formula. I like this one because it's easy to remember. And so very few times I actually do these by hand, I can easily get it. 15 minus 15.125 gives us negative 0.125. And 18 minus 15.125 is 2.875. 17 minus that is 1.875. 13 gives us negative 2.125. And 14 gives us negative 1.125. 16 gives us 0.875. 15 we're already done. That's negative 0.125. 13 I think we're already done. It's negative 2.125. Okay, well we need to square that now. So we x minus x bar squared. So we got negative 0.125 squared. We got 2.875 squared. 1.875 squared. Negative 2.125 squared. Negative 1.125 squared. 0.875 squared. Negative 0.125 squared. And negative 2.125 squared. 0.125 squared gives us 0.015625. 2.875 squared gives us 8.265625. 1.875 squared 3.5156. Why anybody would do these by hand, I don't know. I mean the standard deviation by hand. Head's hurting from just all these numbers. 4.515625. And the odds that I'll screw up one of these is very high. 1.125 squared. Of course, I know I don't need to worry about negative, because when you square something, it's always positive. So 1.265625. 0.875. Didn't I do that one already? No, I guess not. 0.875 squared. We get 0.765625. 0.125 is our first one, which was 0.015625. And 2.125 is this one, which is 4.515625. Okay, now we want to add those together. 0.015625 plus 8.265625. 265625. 3.515625 plus 4.515625 plus 1.265625 plus 0.765625 plus 0.015625 plus 4.515625. What a mess. Let me double check it. 5625, 8.26, 5625, 3.51, 5625, 4.51, 5625, 1.26, 5625, 0.76, 0.765625, 0.015, 4.51, 5625. Enter. Okay. 22.875. So then S is going to equal the square root of what we just found divided by n minus 1. And n is 8, so we'll have 22.875 over 8 minus 1. So let's see, 22.875 divided by 7. And I don't want to round it, so I got 1.807721534. Oh, okay. We have X bar, we have N, we have S. N was 8. Let me jot these down here. Actually, we don't need X bar. What am I talking about? Okay, N is equal to 8. Oh, we need the chi-squares now. So do our picture. Oh, by the way, to do that on the calculator, I'm not going to do it on a separate. I'll go ahead and do it here. That way I can double check my work too. You go and you input your numbers first. So I'll press Stat, Edit, clean out those numbers. So I'll press Delete a few times, clean those out. And we got 15, enter, 18, enter, 17, enter, 13, enter, 14, enter, 16, enter, 15, enter, 13, enter. Now do a second mode to exit out, and now press Stat, right arrow to Calc, enter on one of our stats, enter again. And let's see if I'm right. 1.807721534. Got it right. Pretty long, horrible, but I got it right. Okay. What are we even talking about here? Okay, 90% confidence interval. So that means I'll put 90% here. I split 10% into the tails, so this will be 0.05, and this is 0.05. I don't think we found these already, did we? Nope. Okay. And this again is going to be our right chi-square because it's on the right side. And this one's going to be our left chi-square because it's on the left side. Now our degree of freedom is n minus 1. N is 8, so we got 8 minus 1 or 7. So from our formula for standard deviation, I think that's what it's asking for. Standard deviation. These are the formulas we're going to use. So we need our chi-squares in N and S. Well, this first one here, the right chi-square, the area to the right is 0.05. So I'll come over here, 0.05, this column, and degree of freedom is 7. So I'll come down here, 7 is 14.067. Now for our left chi-square, this one right here, we're going to find the area to the right of it, which is a 0.90 plus a 0.05, so 0.95. So 0.95, I'm looking in this column, degree of freedom 7, and we get 2.167. Okay, now we're ready for our formulas. So our lower bound is n minus 1 times s squared divided by our right chi-square. N was 8. So we got 8 minus 1 times s squared. 1.807721534 squared divided by the right chi-square, which is 14.067. Now our upper bound, we're going to have n minus 1 times s squared over the left chi-square. So we'll have 8 minus 1, 1.807721534 squared over left chi-square, which is 2.167. Okay. So I'll do my second x squared for the square root. Then we got 8 minus 1, which is 7, times 1.807721534 squared divided by 14.067. So we have typed everything in correctly. Press enter. I'll take this 2 decimal places and we go 1.28. Well, I'll do the same thing for the upper bound. I'm going to just do a second enter to bring up the previous entry. And I'll do my left arrow key back. And we want 2.167. 2.167. And enter. And we get 3.25. So our confidence interval is 1.28, comma 3.25. And we're something, 90%. We're 90% confident that the true value of the population standard deviation falls somewhere in this range. And let me save that. There we go. One last thing I want to mention. Comparison notation. For this particular book, and your book may be different, but my left chi-square is this notation, and my right chi-square is this notation. So if you're trying to see how in the world my formulas match up with those, that's the comparison we use. And that's the, let's see, I saved that. That's the end of that section. So I stop the recorders.